In 1718, Blackbeard left the coast of North Carolina and sailed southeast into open Atlantic water. No landmarks, no coastline, nothing but water in every direction for weeks. And he needed to arrive at a specific island, roughly the size of Manhattan, over 3,000 miles away. He found it. The way he did it involved a technique that takes about 10 minutes to learn, but a lifetime to get right. And it starts with holding a piece of string at arm's length and measuring the gap between the horizon and the North Star with your thumb. That's not a metaphor. That's the actual first step. And once you understand what he was doing, the full chain of it, the instruments, the math, the corrections, the things he was reading in the water and the sky that he never would have written down because every other pilot already knew them, the 3,000 miles stops feeling like a miracle and starts feeling like a craft. A dangerous, imprecise, frequently fatal craft practiced by tens of thousands of men across 2 centuries of ocean crossing. There were, by conservative estimate, over 2,500 documented shipwrecks in the Caribbean alone between 1492 and 1800. Most of them weren't caused by storms. They were caused by navigators who thought they knew where they were and didn't. Blackbeard knew where he was most of the time. The question is how. Every working ship of this period carried the same basic toolkit, and none of it worked as well as you'd hope. The compass you already know about. What you probably don't know is that magnetic north and true north are different places, separated by a variable gap that changes depending on where on Earth you're standing. That gap is called magnetic declination, and in the early 1700s, nobody had a complete, reliable chart of how it varied across the Atlantic. A navigator in the Caribbean might be working with a compass that was pointing 8 or 10 degrees off from true north, and he'd have no way to know it from the instrument alone. 8 degrees of compass error, held for 3,000 miles, puts you 400 miles from where you think you are. That's not a rounding error. That's a different ocean. The good pilots knew this. They corrected for it. Imperfectly, using tables that were themselves imperfect. The bad pilots trusted the needle. The bad pilots are why there are 2,500 wrecks in the Caribbean. Then there was the log line. To navigate, you need to know your speed. The solution used on every ship from roughly 1500 through the early 1800s was a wooden board called a chip log, tied to a long rope with knots tied at specific intervals thrown off the back of the ship. You counted how many knots ran through your hands in 30 seconds, using a sandglass for the timer. That count gave you your speed in nautical miles per hour. That is where the word knot comes from. It was a literal measurement. Knots in a rope, counted by hand. The knots were spaced 47 feet and 3 inches apart. The sandglass ran for exactly 30 seconds, in theory. In practice, sandglasses gained and lost time depending on temperature, humidity, how level they were held, and how much sand had clumped. In heavy weather, with the ship pitching and rolling, with cold hands and salt spray, the count was rough. Everything about this was rough. The whole system was rough. What made it work was that pilots cross-checked everything against everything else constantly and learned over years to feel when something was off. The latitude instrument, first the cross staff, later the back staff, eventually the octant and the sextant, measured the angle of the sun or the North Star above the horizon. The principle is straightforward. That angle tells you your latitude, your north-south position on the globe, to within about half a degree on a good day. Half a degree of latitude is 35 miles. Good enough to find a continent, often not good enough to find the harbor you needed. John Davis, who invented the backstaff in 1594, was replacing an earlier instrument that required the navigator to stare directly into the sun. According to Davis himself, this was, and I'm quoting from his 1594 navigational manual, The Seaman's Secrets, a great impediment to the sight. He was underselling it. The cross-staff had been blinding pilots for generations. His instrument let you face away from the sun and measure its shadow instead. It took another 100 years for it to fully replace the older tool. That tells you something about how slowly this world moved and how much was at stake in even small improvements. The technique that held all of this together was called dead reckoning. The name might come from deduced reckoning, dead reckoning, shortened, or it might have always been dead, meaning certain, or meaning fatal. If you got it wrong, nobody is sure. Maritime historians have been arguing about it since the 19th century. The method, you know your starting position, you know your heading, you know your speed, roughly. You know how long you've been sailing. You multiply the time by the speed, apply the heading, and plot a new estimated position on your chart. Then you do it again at the next watch. And again, every 4 hours, through the night, through fog, through days when the sky was closed and the stars were invisible, and you were working entirely from math. Over 6 weeks of ocean crossing, you're making hundreds of these calculations, each one inheriting the errors of the one before it. A small, consistent error in your speed estimate compounds. A persistent compass error compounds. The currents, which nobody could measure directly, push you sideways from your plotted course without leaving any trace in the numbers. The pilots who were good at this were not just good at arithmetic, they were good at reading the ocean for corrections. Watercolor is one. The deep Atlantic is a specific shade of blue-black, close to ink. As you approach the continental shelf, the floor rises and the water goes green, then gray-green. A pilot who had made the crossing a dozen times knew this color shift and used it as an independent position check 100 miles before any coastline appeared. Seabirds, certain species don't go more than 50 miles from land. When you started seeing frigate birds or certain terns, you were close, not close enough to see, but close. The smell of land, pine resin, vegetation, the particular humid earthy smell of a tropical island can carry 20 miles downwind. Pilots in the Caribbean learned which islands smelled like what: flotsam, vegetation, river runoff, sometimes fresh water floating near river mouths. The Gulf Stream was readable as a temperature and color shift long before anyone formally charted it. Benjamin Franklin, who also served as Deputy Postmaster General of North America and was infuriated by how much slower the mail ships ran from England to America than in the opposite direction, eventually figured out that the mail ships were sailing directly against the Gulf Stream because their captains didn't know it existed as a navigable feature. He published one of the first charts of it in 1770, compiled partly from his own observations and partly from interviews with Nantucket whalers who had been reading the current their whole working lives and had never thought to write it down because it seemed obvious. The whalers knew things the naval captains didn't. The pirates often did too. Here is the flaw at the center of all of it. Latitude, north-south position, was solvable, at least approximately. Angle of the sun or the stars, printed tables, some math. Imperfect, but workable. Longitude, east-west position, was not solvable, not in any reliable way. Not for most of this period. The reason is a problem of time. To know your longitude, you need to know the time difference between where you are and a fixed reference point. Greenwich, say, or Paris. Every hour of time difference equals 15 degrees of longitude. At the equator, 15 degrees is about 1,040 miles. To use this method, you need a clock that keeps accurate time over weeks at sea, on a rolling ship, in salt air, through temperature changes from tropical to North Atlantic. The mechanical clocks of the 17th and early 18th century were nowhere near that. A good clock might lose 10 minutes over a long voyage. 10 minutes of time error is 150 miles of longitude error. A mediocre clock was worse. There were other methods proposed: lunar distances, Jupiter's moons, various astronomical observations, and some of them worked, after a fashion, in the hands of a skilled astronomer with clear skies and an hour to spare. On a working ship, in a storm, with a crew to manage and a watch to keep, they were impractical. The result was that every navigator of this period knew his latitude with reasonable confidence and his longitude as an educated guess. He was navigating in one dimension with some precision and in the other dimension with accumulated hope. On October 22, 1707, Admiral Sir Cloudesley Shovel was returning to England from Gibraltar with a fleet of 21 ships. His navigators believed they were safely west of the Scilly Isles, clear of the rocks, on a good approach to the English Channel. They were not. They were directly over the Scilly Isles. 4 ships struck the rocks that night. HMS Association went down in under 4 minutes. HMS Eagle and HMS Romney followed. Somewhere between 400 and 2,000 men drowned. The exact count was never established. It remains one of the worst maritime disasters in British naval history, and it happened not because of a storm, not because of incompetence, but because the longitude problem had no solution yet. Shovel himself washed ashore alive. The story that followed, and this is where history turns into legend, and the line between them is genuinely unclear, is that a local woman found him on the beach, still breathing, and killed him for the emerald ring on his finger. The account comes from a deathbed confession given about 30 years after the event. Whether it happened, nobody can say with certainty. What's not in question is the wreck and the dead, and what came after. 7 years after the Scilly disaster, in 1714, the British Parliament passed the Longitude Act, offering a prize of £20,000, something in the range of £3 million today, to whoever could solve the longitude problem to within half a degree of accuracy at sea. £20,000. In 1714, the prize attracted proposals from scientists, cranks, theologians, and one man who suggested anchoring a fleet of ships across the Atlantic at regular intervals and having them fire rockets on a fixed schedule so navigators could time the sounds. Isaac Newton appeared before Parliament to review the proposals. He told them that most were impractical and that the problem might be solved with a very accurate clock, but that building such a clock for use at sea was, in his opinion, not feasible given the technology of the time. He was wrong, but it took 47 years to prove it. John Harrison was a carpenter's son from Lincolnshire who taught himself clockmaking from a borrowed copy of a mechanics lecture series. He had no formal scientific training. He had no institutional backing. He had no connection to the Royal Society or the Board of Longitude or any of the bodies that were officially working on the problem. What he had was a specific insight that the reason pendulum clocks failed at sea was the pendulum. At sea, the ship's movement made the pendulum swing irregularly, so he built clocks without pendulums, using interlocking mechanisms he designed himself, with components made from materials that expanded and contracted at rates that canceled each other out in temperature changes. His first sea clock, the H1, was built in 1735. It was 75 pounds. It was tested on a voyage to Lisbon and performed well enough to attract attention. He then spent the next decade building the H2 and H3, progressively smaller and more accurate, before concluding that the entire approach was wrong and starting over. The H4, completed in 1759, was 5 inches across. It looked like a large pocket watch. On a test voyage to Jamaica in 1761, running for 81 days, it gained a total of 5 seconds. 1 day is a longitude error of about 1.25 miles. The Longitude Act required half a degree, which is about 34 miles at the latitude of the Caribbean. The H4 beat the requirement by a factor of 27. The Board of Longitude refused to pay him. They questioned the test conditions. They demanded another trial. They suggested that the clock's accuracy might be specific to that voyage and couldn't be relied upon generally. Harrison spent the next decade in disputes with them, running additional trials that also succeeded, while the board moved the goalposts repeatedly. He was 79 years old when he finally petitioned King George III directly. The king, who had apparently been following the case with some interest, reportedly told Harrison, "By God, Harrison, I will see you righted." Parliament awarded Harrison £8,750 in 1773. Not the full prize technically, but enough. He died 3 years later, in 1776, at the age of 82. The full prize was never formally awarded to anyone. Back to Blackbeard. Back to the original question. He didn't have Harrison's clock. Nobody did in 1718. What he had was the standard toolkit: compass, log line, cross staff, charts, and whatever he'd absorbed over years of working the Atlantic and the Caribbean, first as a privateer during Queen Anne's War, and then as a pirate. Most of the famous pirates of this period weren't self-made navigators. They were trained. They came up through the Royal Navy, or the Merchant Service, or privateering, where navigation was taught because it had to be. Bartholomew Roberts, Black Bart, who captured an estimated 400 ships between 1719 and 1722, which makes him the most prolific pirate of the era by a considerable margin, was the navigator on a slave ship when his vessel was taken by pirates. He joined them. Within 6 weeks, he was in command. He reportedly said, when asked why he'd crossed the line, "Since I have dipped my hands in muddy water and must be a pirate, it is better being a commander than a common man. What he didn't say, but what the record shows, is that his navigation was a primary reason he commanded. You didn't put an incompetent pilot in charge of a ship that needed to outrun the Royal Navy. When pirates took a merchant vessel, the charts and instruments were often the first things they secured. A good set of charts for the Caribbean or the Indian Ocean was worth more than a year's wages for a common sailor. The Dutch East India Company was known to send salvage ships to wrecked East Indiamen, specifically to recover or destroy the charts before anyone else could use them. The Portuguese guarded their coastal charts of Africa and Brazil as state secrets for decades. The knowledge of where the reefs were, where the currents ran, where there was fresh water and safe anchorage, that was the real currency of ocean navigation. Pirates who took charts gained something you couldn't buy, routes that the people chasing them didn't know they had. So how accurate were they actually? For latitude, on a clear day with good instruments, a skilled navigator could place himself within 30 to 40 miles north or south. That was reliable enough to be genuinely useful. The standard technique for making a landfall was called running down the latitude. Sail to the latitude of your destination, then turn east or west, and hold that latitude until land appeared. It was slow, it was conservative, and it worked. It was also a confession that east-west positioning was too unreliable to aim directly at a target from open ocean. For dead reckoning accuracy over a long passage, the honest answer is that it varied enormously. A careful pilot in good conditions might arrive within 50 miles of his intended position after a transatlantic crossing. A careless one, or one who'd had 3 weeks of overcast sky and heavy weather, might be off by 200 miles. The 2,500 wrecks in the Caribbean are partly a record of what 200 miles of error looks like when you hit a reef at night. Blackbeard's specific accuracy on that 1718 passage is not something the historical record can confirm with precision. What the record shows is that he moved successfully across large stretches of open water, repeatedly, over several years, without losing his ship to navigational error. Given what we know about the error rates of the period, that puts him in a category of pilot who was doing something right, even if we can't reconstruct exactly what. The 2-mile figure is the version of the story that got passed down. Whether it's precisely true is less interesting than what it describes. A man working a broken system well enough that it didn't kill him in an era when it killed a great many other people. These pilots knew their instruments were wrong. They knew the compass had errors they couldn't fully correct. They knew their speed measurements were rough. They knew their charts had blank spaces and misplaced coastlines and reefs that had never been logged because the ship that hit them didn't survive to file a report. They knew that their position at any given moment was an estimate, and that the estimate was built on top of other estimates, and that the errors were stacking. They went anyway. You can read that as recklessness, or as the callousness of an era that treated sailors as expendable. There's truth in that reading. Sailors were cheap, and the cargo was expensive, and the men who owned the ships weren't the ones who drowned when the reckoning was wrong. But there's something else in it too, something that looks less like recklessness and more like a specific discipline, the discipline of operating carefully and systematically inside a problem you cannot fully solve, of building cross-checks and correction cycles and redundancies, not because they make the problem go away, but because they make it survivable, of knowing the limits of what you can know and developing the skill to work right up to those limits without pretending they aren't there. John Harrison spent 40 years on a clock. The pilots who crossed the Atlantic before his clock existed didn't solve the problem he was solving. They just learned to live inside it. The sea is a place where you find out what you can know, and then you find out how to sail on the days when you can't know enough. The next time your Maps app tells you that you're 12 feet from a coffee shop, take a moment with that. Someone crossed an ocean to earn that convenience, with a sand glass and a knotted rope.